Electronegativity. Although it does sound very similar to electron affinity, you must be careful not to mistake electronegativity for electron affinity. Whereas electron affinity looks at the amount of energy required to remove electrons from an anion, electronegativity tells you rather the strength of an element to attract electrons towards itself. And the idea kind of derives from the bond enthalpies of the diatomic molecules like difluorine, dichlorine, dibromine, diiodine, and even the combinations of the different halogen atoms like uh, monochlorine fluoride or monobromine chloride. Any of those combinations, basically you see here the values for the bond enthalpies of those elements. All right, now the idea is this. When you have the combination of the different elements, roughly speaking, you might expect that, okay, well, if you take, for instance, difluorine and dichlorine, and you look at the values of the bond dissociation enthalpies of the two um, homonuclear diatomic molecules, you might expect that taking the average of those two bond dissociation enthalpies is going to be roughly the bond dissociation enthalpy of the mixed species, let's say the chlorofluorine combination. And if you do that calculation, if you actually take difluorine and dichlorine and add them together and divide by 2, in other words, take the average, and plot the numbers right here, what you're going to see is that the numbers are very different for everything that's not in the diagonal, right? In fact, not only are they different, they are all lower than the actual values that you see for the bond enthalpies of the species that are different. And the premise right here is that the moment you start mixing elements of different kinds with each other, you now have a different tendency of attracting electrons towards one atom versus the other. And the atom that's better at attracting electrons is going to develop a negative charge, partially, not entirely, but partially. And the element that is worse at attracting electrons will develop a partial positive charge. So you basically create an ionic contribution to the bonding just by mixing elements of different kinds to each other. And so this ionic term that I'm including, right, including a constant, has to account for the fact that the actual bond enthalpies of the elements are higher when you start combining fluorine with chlorine, or bromine with chlorine, or iodine with fluorine. And the ionic contribution, you could look at it this way. Now, here's where the electronegativity comes in. Because when you look at the atoms, right, the one that develops the delta plus and the delta minus signs, as you know, depending upon which one is more electronegative than the other, you could define the electronegativity as follows. Simply by looking at the difference of electronegativity of one element to another. That difference is going to be attributed to the partial charge that you're developing on the atom. And the delta minus is simply the same thing as the delta plus, except that it gets multiplied by a negative. So technically speaking, this K times delta plus times delta minus is going to become nothing more than the difference in electronegativities of these two elements squared multiplied by a new constant. Now, I'm going to skip the actual derivation of this number, but the constant turns out to have a value of 96.5. It is related to something known as the Faraday constant, but you'll get to learn about that constant when you get to electrochemistry and future chemistry classes. For now, it suffices to say that yes, this is the value of the constant. Not that it's going to affect too much of our discussion anyway. But altogether, the chi symbol here represents the electronegativity of the element. And the element itself is shown here in parentheses, right? So this will be the electronegativity of element E. This will be the electronegativity of element X. It doesn't really matter which one you place first, because at the end of the story, you're going to be squaring it. And no matter if this ends up being negative or positive, once you square it, you end up with a positive value. But pretty much this electronegativity idea is nothing more than a measurement of the ability of the electron to attract the ability of the atom to attract electrons towards itself. And as the electronegativity increases, the electron attraction also goes up. All right, so let's take a look at the metals. In the case of combining metals with nonmetals, and if we have the very specific case scenario where we use one metal for every one nonmetal, we end up generating this ionic salt, MX. If we apply the bond dissociation formula to determine the enthalpy of the reaction right here, we could look at the summation of the bonds broken minus the summation of the bonds formed. And what you see is that for the bonds broken, you're breaking half an MM bond, and you're also breaking half an XX bond. So notice here that the bond dissociation enthalpies of MM and XX get multiplied by 1/2, and at the same time you're forming the MX bonds. So you're subtracting the bond dissociation enthalpy of the MX bond, the product. All right, but we also know from the previous slide that the enthalpy of the mixed species is given by the average of the bond association enthalpies of the homonuclear diatomic molecules, MM and XX, plus the ionic contribution, which is 96.5 times the difference in electronegativities of the two elements square. And when you substitute the value of delta H mx back into this equation, what's going to happen is that the half delta H mm plus delta H xx will cancel out completely, and all you'll end up with will be negative 96.5 times the electronegativity difference square. And so this is a really nice means of calculating the enthalpy of formation of a salt, but it actually has to be such that these ratios are kept constant. If you change the ratios, then this doesn't exactly cancel out, and you end up with kind of a bit of a mess. So there's some restrictions to this formula, but it's kind of interesting to see that you can actually approximate the enthalpy of formation of a salt simply by using the electronegativity values. Now, speaking of that, the electronegativity values are not necessarily intrinsic to an experimental chemical feature, but it's more like an intrinsic parameter that is used to rationalize which elements prefer to attract electrons, which elements tend to give away electrons. And so here we're presenting the electronegativity table, the Pauling electronegativity table. And one thing that you can see is that from top to bottom, the electronegativity tends to decrease. We can see that for the alkali metals, and we can see that for the halogens. And this is happening because the radius of the element is increasing, the electrons are getting further away, so there is less of an effective nuclear charge attracting electrons. So there's not much of a tendency to attract electrons as you go down a group. But when you go from left to right, you see a regular increase in electronegativity as you go farther and farther to the right. And by the time you get to the halogens, you reach some of the highest values. Specifically, fluorine is the highest value in electronegativity. And that means that fluorine is very prone at taking electrons away from any other atom. Oxygen is kind of second on that list. And the reason that's happening is because the effective nuclear charge is increasing as we go from left to right. Alright, so there is an approximation associated with this process. And I will not only tell you what the approximation is, but I'll show you an example of it in the next video. So see you there.